Welcome to the 32nd lecture of the MOOC on parallel algorithms. Today we shall see some more results on a wrap butterfly and cube connected cycles. A wrap butterfly and in consequence a butterfly and as well as a cube connected cycle are quite versatile networks. The result that we are going to show is that any general network, interconnection network of a constant vertex degree can be simulated on a wrap butterfly at a low cost. We shall see what the low cost is. So, we assume that we are given a general interconnection network. Let us say we have a network of n nodes, where n is r times 2 power r for some r, or n is less than or equal to that. Let us take a wrap butterfly of r times 2 power r nodes, and we want to simulate the algorithm that is given for the network on the wrap butterfly. So, we have a generic network and we have some algorithm given on this generic network. We want to simulate this algorithm on a wrap butterfly. That is the problem at hand. So, the first thing that we do is to map the nodes of the network. Let me call the network G onto the wrap butterfly 1 to 1. This 1 to 1 mapping could be anything. So, what we do is to map the vertices of the given network onto the vertices of the wrap butterfly anyhow. The only requirement is that it has to be a 1 to 1 mapping. And then consider a step of the given algorithm. This given algorithm runs on G. So, let me call it the G algorithm. So, we consider a single step of the G algorithm. As is customary in all interconnection networks, what we assume is that in a step, each node of G communicates to all its neighbors. A node has a constant number of neighbors. Let us say the vertex degree of G is D, the maximum vertex degree in G is D, which means a node can have at most D neighbors. So, in every step of the algorithm, a node may have to communicate with all its D neighbors. So, a node has D messages to send and D messages to receive for each node. So, that is the constraint we have. These many messages have to be transferred. Once we have a way of transferring all these messages, then we can say that the step is simulatable, because we have mapped the nodes 1 to 1. We have one processor for every node of G. So, the internal computations can be done by the assigned processor, but once the messages are handled, then we would have achieved the simulation. So, the second step is to color the edges of G using D plus 1 colors. The given graph G is a generic graph. So, we do not know the minimum number of colors required to edge color the graph, but in any case for a D degree graph it is possible to edge color the graph with D plus 1 colors. So, that is what we are going to do. We will color the edges of G using D plus 1 colors. Now, this coloring is done once and only once. So, this is an offline operation. Therefore, we could do this sequentially. So, we are not going to count this in the cost of our parallel algorithm. We somehow edge color this network G using D plus 1 colors, and then consider each color class separately. A color class is the set of all edges belonging to the same color. So, in particular, if we consider all edges of color 1, they form the color class 1, and we know that they form a matching. No two of them can be adjacent. So, each color class forms a matching. So, our idea is to simulate the message passing step using D phases. In each phase, we handle one color class. In each phase, we handle one color class. So, there are D phases. So, when I consider one particular color class, we find a matching. So, the edges of the matching could be like this. So, if the vertices are labeled in this fashion, what it means is that A has a message to send to B and possibly B has a message to send to A. So, the messages between A and B will be exchanged in this phase. At the same time, the messages between C and D will be exchanged in this phase, and so on. So, all these edges are of the same color. Therefore, the messages that should pass through these edges will be handled in the first phase. This, let us assume, is color class 1. When we consider another color class, of course, no two of them could be adjacent. So, blue is another color class here. This possibly could be the second color class. So these edges could be considered in the second phase. So in the second phase, we will exchange the messages that are between B and E, C and F, D and I, and H and J. So in this manner, we will consider all the color classes. Once all the color classes are considered, we would have considered all the edges. So all the messages that are destined to be delivered by every single edge would be delivered at the end of the simulation. So we have D phases to the simulation. So now let us consider any single phase. In particular, consider the first phase, in which we consider color class 1. What matters is that we have a matching. No two edges of the same color are adjacent. So this forms a matching. So let us consider the edges of color class 1. The messages on these edges have to be delivered, but how would we deliver them? In our example, we find that A and B belong to color class 1, so do EF, CD, GH and IJ. These edges all belong to the same color class, let us say color class 1. So these edges are active at the moment. But A and B are adjacent in graph G, but that does not necessarily mean that the vertices that are mapped to A and B in the butterfly network or the wrap butterfly network are adjacent to each other, because what we did initially was to map the vertices of G anyhow to the vertices of the wrap butterfly, a wrap butterfly with at least as many vertices. So it is not necessary that A and B are adjacent in wrap butterfly, but we still have to send a message from A to B. How do we do this? So now if you consider a wrap butterfly, if I do not draw the edges, what we find is that there are 2 per r rows and r columns. Now the situation that we have is this: we have a message sitting at each vertex. If this is A and this happens to be B, there exists an edge between these two in graph G, but this edge is not present in the butterfly network. Now we have a message from A that should be going to message B. So we have essentially a routing problem on the butterfly network. On the wrap butterfly of diamond of size 2 per r by r, we have a routing problem. Every node in the wrap butterfly network holds a message, and every message has a unique destination. So the question is, how do you deliver the messages? Looking at the nodes of the wrap butterfly gives us an idea. When we look at the nodes of the wrap butterfly, we find that they are arranged much the same way as the nodes of a mesh. A 2 per r by r mesh would have the nodes arranged exactly the same way, only that the edge sets would be different. But then there is some similarity in the edge sets too, because the horizontal edges in a wrap butterfly are exactly the way they are in a mesh, except in that there is a feedback. The last node is connected to the first node. Except in that a wrap butterfly is very similar to a mesh. But then the cross edges here are quite different from the vertical edges of the mesh. In a mesh, we have edges which are vertical. For example, we have edges of this sort in the mesh. These edges are missing in a wrap butterfly. So we have an arrangement of the processes that is very similar to that of a mesh, but the vertical connections are missing. Instead of the vertical connections, what we have are the cross connections. Now the question is, using these cross connections, can we actually manage to transmit the messages using the messages vertically? Let us consider recall the algorithm for transmitting messages on the mesh. This mesh routing algorithm had some offline computation which wasn't to be executed in parallel necessarily. So the offline computation could be executed sequentially too. So we are not going to delve on that. The online computation involved essentially transmitting messages along the rows, followed by transmitting messages along the columns, and then again along the rows. So the mesh routing algorithm had 3 phases. In the first phase, we transmitted the message along the rows. In the second phase, we transmitted the messages along the columns, and in the third phase, we again transmitted the message along the rows. Now we find that here transmitting messages along the rows is easy enough, because every row has connection using straight edges. We have a connection of this sort exactly as in the case of a mesh. So steps 1 and 3 can be executed exactly as it is. These executions will take order of r time. What remains is the vertical communication along the columns. If we had vertical connections of this sort, that is, had our network been a 2 power r by r mesh instead of a wrap butterfly as it is now, then it would have taken 2 power r steps to do the vertical communications. But then if n equals r times 2 power r, then r is theta of log n and 2 power r is theta of n by log n. Therefore, the time taken would have been order of n by log n. We would have had only an order of n by log n time simulation of every single step, which is not good enough. That is why we are not attempting the simulation using a 2 power r by r mesh. Instead, we are considering a 2 power r by r wrap butterfly, which is an r dimensional wrap butterfly. So now the question is this: how do we achieve the vertical communication along the columns? In particular, let us consider the 0th column. So in the 0th column, we have 2 power r nodes, and each of these nodes holds some messages, and these messages have to be communicated vertically. How would we do this if we had a Benesch network instead of a wrap butterfly network? As we saw in the last class, given any permutation pi of the input values, Benesch network will allow us to communicate to realize this permutation using edge disjoint paths. So that is the technique we would use here. So if we had a Benesch network instead of a wrap butterfly, we would be able to place exactly these packets here, the packets belonging to the 0th row, as inputs to the Benesch network, and then with an appropriate configuration we would be able to deliver them here after 2r steps. So given these permutations, we would be able to compute the necessary configurations of all the switches here. So if you assume that every Benesch network switch is a reconfigurable switch, then we would be able to compute the reconfiguration necessary for the switches, so that the transmission could be achieved in 2r steps. This is what we saw in the last class. So for any fixed pi, there is one reconfiguration, and this reconfiguration could be computed and implemented. Once it is implemented, the delivery of the inputs would be achieved in 2r steps. So now we have 2 power r packets that are to be delivered to the same nodes. But then we do not have a Benesch network, all that we have is a wrap butterfly. But then a Benesch network is nothing but 2 butterflies pasted back to back. So in a wrap butterfly, if I start with the 0th column, suppose this is the 0th column, if I send the messages forward until they come to the 0th column again, which also happens to be the last column, and then allow the messages to be sent back in the reverse order until they come back to the 0th column, we would have achieved the effect of a Benesch network. All that we have to do is to reconfigure the switches accordingly. So we take the Benesch network, the imagined Benesch network that is necessary for delivering the messages with the permutation realized, divide the Benesch network into 2, see that there are different configurations. So this is config 1 and this is config 2. Configure the switches according to config 1 and then send the messages forward until they complete one full revolution, and then change all the configurations to the second set and then send the messages back. We would have achieved the same result as we would have sent the messages through a Benesch network. So we are essentially simulating a Benesch network using a wrap butterfly network. In a wrap butterfly, every message going clockwise once and then counterclockwise once will have the effect of passing them through a Benesch network. So using the result of the previous class, we will be able to make sure that every message of the 0th column is delivered to the correct destination. Now you should remember that a wrap butterfly is in fact a rather tall cylinder. It has a height of 2 power r whereas this is only R. Therefore, the time taken for 2 revolutions is order of R. In order of R steps, we manage to send all messages which are in column 1 to their correct destination. So, we manage to permute this column in order of R steps. So, there are 2 power R nodes here, they get permuted the way we want in order of R steps. So, in a mesh, what would have taken 2 power R steps is achieved in order of R steps here. But then this will ensure the permutation only of column 0. But then what about the remaining columns? Columns 1 to R also have to be permuted the same way. How would we handle them? To handle these columns, we use pipelining. Exactly analogous to column 0, column 1 also can be permuted this way. You start from column 1 and do 2 revolutions. Let us say this is column 1 and this is column 0. I will use 2 different colors to explain what is happening to column 1. Column 1 makes 1 full revolution and then goes back. Once this is done, column 1 would have been permuted. Column 0 can be handled as we said before. From column 0 we do 1 full revolution and then go back to make sure that column 0 is permuted. So, we can compute the configurations that are necessary for the column 0 permutation as well as the column 1 permutation and by extension for every single column. But then what we find is that the rotation for column 1 is 1 step ahead of the rotation for column 0. Therefore, when column 0 is configured using the configuration requirements necessary for revolving the column 0 elements, column 1 could be configured the way it is necessary for permuting the column 1 elements. So, we have several permutations going on at the same time. We have pre-computed all the configurations that are necessary to achieve each of these permutations and then we interleave them appropriately. That is, the first step of all these configurations are picked out and these configurations are adopted throughout the cylinder. So, when column 0 is adopting the configuration that is necessary for column 0 permutation, column 1 is adopting the configurations that are necessary for the first step of the column 1 permutation and so on. After that, these configurations will slide by 1 position. Column 0 permutation will move on to column 1 while column 1 permutation will move on to column 2 and accordingly we will pick the permutations. So, all these permutations are rotating simultaneously. So, when column 0 completes 1 full revolution, column 1 also would have completed 1 full revolution, only that the column 1 revolution will always be 1 column ahead of column 0, but then the completion of the revolution happens exactly at the same time. So, what happens is that all these permutations are rotating simultaneously, complete the revolution simultaneously and then rotate back simultaneously. So, when 2 revolutions are complete, we would have achieved the permutation of every single column. So, in order of R steps, using pipelining as I explained just now, all permutations can be executed. So, now putting it all together, what we find is that the routing problem on the wrap butterfly runs in R plus order of R plus r steps, which is order of r steps. But then remember, we have an n node wrap butterfly. Therefore, the dimension of this wrap butterfly is order of log n. Therefore, this routing problem executes in order of log n time. Now, this routing problem was the key to sending the messages. We are now considering one particular color class of the original interconnection network. So, all the messages of this one single color class can be delivered in order of log n time. Then consider all the color classes. We have D color classes. Therefore, in order of d log n steps, which is order of log n if d is order of 1, all messages of the step are delivered. So, once the messages are delivered, to complete the step, all that is necessary is to do the internal computations. Since we have exactly as many processors in the wrap butterfly as there are in the given network, the internal computations can all be done in order of 1 time. Therefore, one step of G can be simulated in order of log n steps in the wrap butterfly of dimensions log n. In other words, a G algorithm that runs in T steps runs in order of T log n steps on our wrap butterfly of the same number of nodes. So, this establishes that the wrap butterfly is a pretty generic network, and by extension, if a wrap butterfly can do this, a butterfly can do this, and also a CCC can do this. All these networks we have seen are quite similar to each other. Therefore, what we do in one can be simulated on the other in order 1 extra time. Therefore, in all these models, a G algorithm that runs in T steps can be simulated in order of T log n steps. So, all these are pretty versatile models, and they also have the additional advantage that the maximum vertex degree of a node is a constant. It is either 3 or 4. In comparison, a hypercube has vertex degrees that are quite large. On a hypercube of n nodes, the vertex degree is log n. So, that is the advantage of these networks over a hypercube. Now, we shall see another network which is also closely related to a hypercube and has several nice properties. This is a shuffle exchange graph. In a shuffle exchange graph of dimensions r has 2 power r nodes. We assume that the nodes are numbered consecutively using binary strings starting from all zeros to all ones. So, there are 2 power r binary strings of this sort. So, the nodes are labeled in this fashion, and using these labels we can define the adjacency of a shuffle exchange graph. There are 2 kinds of edges in a shuffle exchange graph. There are exchange edges, and exchange edges between a vertex of this form and a vertex of this form. That is, a vertex is adjacent to a vertex whose label is identical to every bit except the least significant one. So, if two nodes differ exactly in the least significant bit, then they would be adjacent using an edge called an exchange edge. The second kind of edge is called a shuffle edge. A shuffle edge is where we cyclically rotate the representation. U1 through UR is adjacent to U2 through UR and U1, and by extension it should also be adjacent to U1 through UR minus 1 and then UR coming in the beginning. We are now right shifting the bits. So, this is a right shift and this is a left shift. So, from a node there could be two such shuffle edges. Let us consider a three-dimensional shuffle exchange graph. In a three-dimensional shuffle exchange graph, we have adjacencies of this sort. The dotted line represents an exchange edge. A three-dimensional shuffle exchange graph looks like this. So, this is an exchange edge between 000 and 001, and this is also an exchange edge between 110 and 111. This is an exchange edge between 010 and 011. 100 and 101 are also connected using an exchange edge. So, you can see that in all the exchange edges, the two end nodes differ by exactly the least significant bit. In shuffle edges, we perform cyclic rotations. When we perform left rotations, 001 becomes 010, and when we rotate again, we get 100, which we rotate again to get 001. So, when we cyclically rotate to the left, we will be going through this cycle 001, 010 and 100. Similarly, in a mirror image situation, when we start from 011 and do a left shift, we will be going to 110. Another left shift will take us to 101. Another left shift will take us back to 011. Right shifts will take us through the cycle in the opposite direction. Now, 111 when is subjected to a cyclic rotation will give us 111 again. So, there is a shuffle edge from 111 to itself, and also a shuffle edge from 000 to itself. So, this is a three-dimensional shuffle exchange graph. This graph also has several nice properties. In particular, it has a small diameter. Let us say we want to go from U1 through UR to V1 through VR on the shuffle exchange graph. There could be several such paths, but we would demonstrate one such path, which is of length order of log n. So, we start from U1 through UR. Let us say we do a shuffle, which will take us to U2 through UR and U1. So, a shuffle edge will take us from U1 through UR to U2 through UR, U1, and then we take an exchange edge to go to U2 through UR, V1. This exchange edge is optional. If U1 is identical to V1, then we do not have to take this exchange edge. If U1 is identical to V1, then these two vertices U2 through UR, U1 and U2 through UR, V1 are identical. So, we do not have to take the exchange edge. So, this exchange edge is optional in our path. So, using this exchange edge, if necessary, we have now reached U2 through UR, V1. If we perform another shuffle, we will come to U3 through UR, V1, U2. Then again let us take an exchange edge to come to U3 through UR V1 V2. This exchange edge is also optional. Then again we will take a shuffle edge to go to U4 through UR V1 V2 and U3 and so on. Finally, with an optional exchange edge, we will end up converting every bit to the V's. That is, starting from U1 through UR, we will end up reaching V1 through VR. So if you take shuffle and exchange edges in this manner, we will be able to go from any vertex U1 through UR to V1 through VR. In the worst case, we will have to take an exchange edge for every single step. So even if we take the exchange edge in every single step, the path has a length of 2 log n. To R in this case, since R equal to log n, the length of the path is 2 log n. So with a shuffle edge and an exchange edge, we are fixing every single fixing a single bit. So with 2 log n steps, we will be able to fix every single bit. We will be able to transform the label from U1 through UR to V1 through VR. So in particular, if Vi is the complement of Ui for all I, then 2 log n steps are necessary to achieve this transformation. But that is the worst that can be. Therefore, from every vertex in the graph you can go from any vertex to any vertex using at most 2 log n steps. And the maximum will be taken when the source and the destination are bitwise complements of each other. For example, here, if you want to go from 00 to 111, you can change the bits one at a time. You perform a shuffle edge, you take a shuffle edge, come back to 00, 000, and then take an exchange edge. So you will start from 000, the shuffle edge will take us to 000 again, then exchange edge will take us to 001, then one shuffle will take us to 010, exchange will take us to 011, and then another shuffle will take us to 110, and then an exchange will take us to 111. So this is a path of length 6 from 000 to 111. You can see that this path is not necessarily the shortest possible path in the graph, but such a path certainly exists. So what we demonstrate is that for any vertex U1 through UR and V1 through VR, there is a path of length at most 2 log n between these two vertices. In other words, the diameter of a shuffle exchange graph or when we consider a shuffle exchange graph of n nodes, the diameter is theta log n. That establishes that the diameter of a shuffle exchange graph is low indeed. We shall see more properties of a shuffle exchange graph in the next lecture. That's it from this lecture. Hope to see you in the next. Thank you.